Hey, good to see you, everyone. Nice to be here. Really pleasure to be here. I was at GGI once before. I had to go to my records and look it up. It's 16 years ago. And it's really good to be back. I will talk about DESI results. Immediately, I should say that Satya did me especially a big favor by covering DESI already in quite a bit of detail. So I will very briefly review science of DESI very, very briefly, and then I'll give some opinions that are not just my opinions, they're really heavily informed by my discussions with the DESI analysis team about trying to understand what this data means, and in particular, what's true for sure and what's we are not so sure about regarding DESI data. And I've heard by osmosis, both here in GGI and elsewhere, lots of questions. Is your parameterization good? What do you really measure? Is this data point wrong? So I will try to address those points with extent possible. I co-coordinated year one analysis of DESI, and of course what I'll discuss is not year one, but year three of so-called DR2, in which many people participated. So just for some quick introduction, this audience is quite sophisticated, so I only left a few slides. The discovery of dark energy, which in itself is a really very interesting story, is a talk of its own, but using type 1a supernovae in the late 1990s, I was in graduate school then, and I really like this graph, which is both popular and technical. So this is the distance modulus, the changes in distance modulus of the y-axis as a function of redshift, and this is real data as of very recently. It's not individual supernovae. Each data point is a combination of 20 supernovae or so. And then there are some select sample theory curves for matter-dominated universe of different geometry, as well as our favorite lambda CDM cosmology. And you can see that lambda CDM fits and the green curves don't. Now, the fine print here is that actually all of these curves are able to float up and down, corresponding to the unknown absolute magnitude of supernovae. And so it's not as easy as saying they are very, very far away from the data. But so we are really looking for curvature in the data, and curvature in the data is such that neither of the green curves nor many, many others that you could make fit the data, but rather something like the blue curve where universe accelerates now and decelerated in the past. And that's, of course, led to a very familiar picture with 3/4 dark energy and 1/4 dark matter. Over the years, the constraints on dark energy, particularly equation of state W, have shrunk, and they used to be pretty broad. The first paper that did measurement of W with modern data, to my knowledge, is Garnovich et al. This was a high Z supernova team, I think 99, and there was very broad constraints. They shrank and shrank around the value of -1, which is, of course, special value. It's a value for the cosmological constant. And I will discuss how this changed, how this evolved, this finding in the recent past. This is the, I'm going to talk immediately, jump into DESI data and combine data. And this is, of course, a telescope at Kitt Peak. And my experimental colleagues tell me that the telescope itself is not super special. It's, a good telescope, but it's not the biggest. It's pretty old. But what is really special is instrumentation that was put onto the telescope. And that led to this really fantastic achievement of getting up to 100,000 spectra per night. So I remember when I was in grad school and maybe early postdoc, and there were few redshifts, and then at one point, Sloan had 1 million redshifts. They have 1 million redshifts. Well, 1 million is a lot. So you can see that 1 million redshifts for DESI is 10 good nights of observation. So it's really, I think in the first 2 months, DESI exceeded all the redshifts ever taken. So it's really working really, really well. And this is where really, again, Satya did me and all of us a big favor. She discussed in detail instrumentation that was put on DESI, the tracers, bright galaxies, luminous red galaxies, emission line galaxies, quasars, and Lemon alpha forest, the physics of the BAO, and she also discussed in quite a bit of detail cosmological constraints. So her talk was 2 weeks ago, and you can see the video and the slides on the GGI website. So I will very briefly touch upon a couple of these things and discuss results and keep this whole thing short so we can discuss a bit and then do other things. So one thing that I think Satya has not shown is University of Michigan's claim to fame. Now, most things were built at the Berkeley lab, but this thing was actually built at Michigan, literally 2 or 3 doors away from my office. This is fiber positioners. These are little sticks the size of a pencil, and there are 5,000 of them, and this is the movie visualization of how they look. They each point to a galaxy. Those galaxies were previously selected. They take spectrum of that galaxy, 5,000 spectra, and then they go bzzk, they move to a new position, 5,000 spectra, bzzk, new position. About half an hour takes to take spectra, and 5,000 by 5,000, this is how you get to up to 100,000 spectra per night. This effort was Professor Greg Tarle and research scientist Mike Shubnell and the whole team, and they assembled these by hand. And they told me it was quite a challenging problem. If you had 5 million fiber positioners, you would have built a machine to build them according to them. But 5,000 isn't quite really enough. So they built them all by hand, and there was something like 120,000 parts that had to be assembled by a small army of undergraduates and temporary employees. And so that thing is working really well. That's fiber positioners. This is really at the core of the success of what DESI was able to observe. This is my research group at University of Michigan. Almost everyone in this picture is working on some aspect of DESI, and depending on your age and what conferences you went to, you probably know some of these people. Some of you, Wendert Andrade, postdoc graduate student Otavio Alves, Johannes Lange, who is now professor at American University in Washington, D.C. And Wendert, I'd really like to highlight his major contribution to DESI. He co-led the DR2 BAO measurement. So BAO measurement and all of the tests associated with that, which is most of the work, because in comparison, cosmology analysis, in my opinion, is fairly straightforward. But what's not straightforward is to do all those tests, and he was one of the, I believe, 3 people leading that for DR2. This, again, the sample in DR2, which is 3 years of observation, is much bigger than in DR1, 1 year of observation, more than double. And I have here some numbers, 2.4 improvement factor in the data volume. So it's really a pretty major shift. And this is the BAO. I think this is the only slide I have on BAO. I don't think I need introduction for this audience. It's been introduced already. There are these slight wiggles in the power spectrum. Zoomed in, they look like so. If you looked in configuration space, they look like one peak. They were first discussed by Sunav Zeldovich in the year I was born, 1972. And yeah, that's the baryon acoustic oscillation. And now I do want to say one thing. I know there are some theorists here, and a lot of this might be familiar, but what is important and maybe not familiar to literally everyone is, okay, so this is still a known fact that we are observing, the sky doesn't look like this, but we are observing excess probability flow clustering, and this feature that's, 150 megaparsecs co-moving, but really we are observing the angular extent of that feature at the distance to that sample of galaxies. So we really have this triangle in which we measure angle, and so therefore we measure the ratio of the sound horizon to the distance. And so if we have a little bit of prior on the sound horizon, we measure distances. But fundamentally, what comes out of the box without any prior is this ratio of distance to the sound horizon. And I didn't write down formula for sound horizon here, but let me immediately say, we need the baryon BBN prior from nucleosynthesis on omega BH squared. And with that prior, you can basically solve for RD, and then you just get distances. So all of the interesting cosmological results start once you just need this BBN prior, and then you're ready to start getting results. And the one thing that I wanted to mention here that's just in case it's not super familiar is that there are 2 kinds of distances. I'm going to shake my stick here. Perpendicular to the line of sight and parallel to the line of sight. And of course, pairs of galaxies can be at an angle, in which case you project to either perpendicular or parallel. So for any sample of galaxies, we don't quite have one measurement of this distance divided by the sound. We have 2 measurements, perpendicular and parallel to the line of sight. And so sometimes we don't do it that way. Sometimes you kind of orthogonalize that basis, and you talk about the average isotropic distance and then the ratio of the transverse and line of sight galaxies. But we have 7 samples of tracers, and so therefore we don't quite have 7 measures of this. We have 14 measures of this, just because we have parallel and perpendicular to the line of sight. And just kind of finishing up on this background through which I'm going pretty quickly, we have, so these are the 7 tracers. There should be 7 circles here. Top panels is monopole, lower panels is quadrupole of clustering. Mainly the monopole has the high signal to noise. And the circled things are things that we ended up using the analysis. You can see the individual tracers, but you have a weird thing like a combination of LRG and EL in bin 3 and ELG in bin 1, which has better signal to noise than just ELG1. So what exactly was used is the subject of this Andrade et al. Paper. It's a 50-page, really painful paper, really essential paper for this, to do blind tests and first test on mock data, then test on blinded data, and make sure that many checks are passed. And then only once these things are passed, then also we're able to let these go into the further analysis and also kind of make these decisions what's to be used. So really most of the work was in this, you could call it validation, which is not very cool to talk about, but it's really, really essential for this work. So now I'm going to discuss in order results. I'm going to discuss 3 featured results and spend extra time on the dark energy because that's the one that got by far the most coverage. So the first of the 3 featured results, yes, question. A good question. There was some stuff discarded, although if you look here, almost everything belongs somewhere. So in DR1, like one of the ELG bins was certainly discarded. Now all of the ELG is in. So I'm not actually sure. I don't know if Satya knows if anything was actually discarded in DR2. It's a detailed question. Almost everything was used, or literally everything. One of the two. I'm not sure. Oh yeah, right. Oh, that's right. BGS quadrupole. Yeah, you can see what's not circled here. That yeah, BGS quadrupole. Yes. Yeah, I cannot explain what the shape of the Lyman alpha cross Q is. So no, sorry, I cannot. I do see a BAO feature here, and this I cannot. No, I don't. Okay, Satya can. Oh, that's a really nice explanation. Thank you. People who watch the video won't have heard what Satya said, but she had a very nice explanation about why this has a shape. Since I'm moving into results, any other questions about data? Although I'm the wrong person to ask, but any other questions about BAO or data or galaxies? They are autocorrelations. So this is BGS. That's a very good question. It's not a silly question at all. This is a BGS with BGS, LRG with LRG, this with, every. Now the cross correlate, you could ask, why don't you cross correlate this sample with that sample? And I believe that we didn't do that because, okay, somebody correct me if I'm wrong. I think we didn't do it, and that's because it doesn't add much information. Because in this business of spectroscopic modes that correlate different redshift bins are small. So primordial non-Gaussianity actually would correlate different redshift bins. But like cosmological parameters, I think they're mostly uncorrelated. I believe that's the explanation why we don't use it. If you want to do complete thing, you can do, but I think we have we have checks that show, and it also makes sense that you get very little improvement if you do cross correlations as well. So for now, autocorrelations. Good question. Yep, that's a good question. Okay, I will move to featured results, and I'll cover 2 of them briefly, and then I'll talk about dark energy for a bit. So first featured result, Hubble constant, 68.5 plus minus 5, DESI and BBNLO, no CMB. So without CMB, we get H naught in the 60s. This had to be the case. This I completely expected we were going to get H naught in the 60s. Would have been huge surprise had we got H naught to be like 73, because all the global probes, that is probes of Z less than very small, greater than very small, they agree that H naught is in the 60s. And actually, it's interesting that we got 68.5, not 67.5 like the CMB does. And you can see that's a subject of a little bit of tension here. CMB gets 67, we get 68. And that's an interesting thing to discuss. There's a mild tension there. But the 0th order statement is we agree with the CMB. And that had to be the case, would have been a huge surprise had we got something else. And that's, again, not that CMB should be doubted, but independent of the CMB, we observe the Hubble tension, right? We get H0 in the 60s that conflicts with local measurements, even without CMB. So that's really nice to see. Again, not that anyone doubts the CMB, but good thing to get. That's featured result number 1. The question is with fixed neutrino mass? I'm blanking because in DES we varied neutrino mass. Here, I think, on the spot I don't remember. I think it also doesn't matter too much if neutrino mass is varied or not. It's a good question. I think we vary neutrino mass. Neutrino mass is an extension, so I think this is with fixed neutrino mass. Yep. Yeah. Yeah. Oh, the CMB. Yes. 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 That's a good point. Yep. Hubble constant 68. Featured result number 2, neutrinos. So it's a fun fact that neutrinos are non-relativistic today, and it's really, I usually think of neutrinos as a very relativistic particle, but the universe is so cold today that neutrinos are non-relativistic, and therefore they contribute like matter. They contribute to omega matter. So omega matter is a sum of baryons and dark matter, and now neutrinos. And so this is the only way in which BAO is sensitive to neutrinos. Once you add full shape, you start getting effect of neutrino suppression. That was small amount of information in DR1. In the forthcoming DR2, we hope and expect to have more information on neutrinos from structure formation. But for the moment, this is just a constraint from geometry. And this is a constraint you've all seen this. This is omega matter, neutrino mass on the y-axis. DESI constrains omega matter. And to the extent that it cuts through the CMB contour at the very edge, that is to say that omega matter favored by DESI is a little bit smaller than omega matter favored by CMB, you get this kind of a sharp cut at the edge. So you get a very low upper limit on the mass of neutrinos. And that upper limit is this number. Had we got slightly higher omega matter, we would have gotten looser constraint on the neutrino mass. And of course, if you go to W0, WA, for example, you get quite a bit looser, but still a tight limit on the neutrino mass. This is a very small number regardless. It's just incredibly small number or very, very small number if you take in lambda CDM and combine DESI. And you could say this is due to omega matter, but I would flip that argument around. You could also say if neutrino mass is really low, then this is precisely the kind of thing you would be seeing. You'd be seeing kind of lowish omega matter from DESI compared to CMB. So, I don't know what's a chicken, what's an egg, but, it's a chicken and the egg problem, but the two are correlated, the two statements that omega matter is low and neutrino mass is tight. And this is a posterior, again, people have seen this, posterior on the neutrino mass as a function of mu. A few comments here, hierarchies are not ruled out, but they are coming under tension. The neutrino limit is looser if you do W0, WA. And for the life of God, people, neutrino masses are positive. It's not negative. It can only be positive. It's MC squared. The data are perfectly happy with a positive neutrino mass. And I've heard now many times people talk about negative neutrino mass. I've waged that battle in DESI. I lost clearly. I resoundingly lost because now a lot of people are, extending this to the left is unphysical. I don't think it makes any sense. The ansatz you need is completely made up. So anyway, just my opinion that the data are happy with positive but very low neutrino mass. That's a second result of the feature 3. And now I'll talk about dark energy. Right, so we've seen this, lambda CDM, DESI data, DR1 and DR2 shifted. And if you don't work in this corner of cosmology, let me just say that this is a very, very challenging parameter space to constrain, really very challenging. There's a ton of degeneracy in this. And so the fact when we unblinded the, DR1 even, I was really kind of stunned to see the DESI contour alone be something that doesn't fill most of the space. It's skinny and long, this contour. And that alone tells me that the data are very constraining because this is a very, very challenging parameter space. Oftentimes you have some model with many nuisance parameters in lambda CEDM, and as soon as you get these two parameters on top of the n original parameters, you get a ton of degeneracy. So this is really sign of the good things to come, that the DESI alone looks like this. DESI plus CMB is, I think, 3.1 sigma away, so this is no supernovae from the standard model, and you've all seen this when you combine with one of the data sets. You get, depending on which supernova data set, you get 2.8 to 4.2 sigma departure. This is all shown many times, so I'm just kind of going through this fairly fast. One thing that I'm not sure how often it's, one piece of mind about the robustness of this is if you don't do CMB at all, not that you would doubt CMB, but this is no CMB. This is DESI plus dark energy survey year 3 3x2 analysis. So this is a combination of galaxy clustering and weak lensing with or without supernovae. And this is galaxy clustering and DESI with supernovae. This is no supernovae. So this is only DESI and DES clustering and lensing. And so this is no supernovae and no CMB. And you still get some kind of more than 2 sigma tension with lambda CDM. So this is really showing that there's more than one independent piece of information that hints mildly, perhaps, toward this tension with lambda CDM. It's not just one thing. It's not just supernovae are wrong. Well, they're probably not wrong, and also you can take them out and see that. So tantalizing hints of departure. Well, let me just move on here, and people can ask questions if they have. So with my graduate student Prakhar Bansal, we try to understand a little bit better. We were hoping to understand what's going on fully. I don't know that we succeeded, but we did some tests. So we considered a model that has a lot more freedom in the H of Z expansion. And there are 4 panels here. Don't worry about them. Just look at one panel. They're all similar. They're different data combinations. So in this panel, the vertical axis is H of Z relative to lambda CDM. So horizontal line of 1 is lambda CDM. The smooth curve in orange is W0, WA, best fit model, and then the 68% region. And then the pink curve that's very jagged is this much more complicated model with, I think, 6 free parameters that allows a lot of freedom in the expansion history. And the kind of stunning thing about this, in my opinion, is that this much richer model does exactly the same thing as W0, WA. It goes up, it goes down, it overshoots, it undershoots. So it has a very similar behavior. Its goodness to fit is obviously not very much better at all than W0, WA. So this model is not favored by the data at all. What this says is W0, WA is a really good fit to the data, because even if you allow a lot more freedom, you get the same thing. So I'm paraphrasing Eugene Wigner here. There's like maybe an unreasonable effectiveness with which W0, WA fits the data. And so along those lines and questions of parametrization, we had this supporting paper in DESI, Loda et al., where we try many different parametrizations. And, binning, this is binning in W of Z for bins. There's Gaussian processes. There's this parametrization, that parametrization. They all give qualitatively the same result. So here's an example from this binning. You see overshoot and undershoot, universe W greater than -1 and the phantom regime. And the error bars are much bigger, so the significance here is not as big. But in almost every case, we get qualitatively the same thing. This tells me that this result that we have is robust with respect to parametrization. And so I've heard the people ask, is W0, WA a good model? Should we really use that? I think it is a good model. But even if you don't think it's a good model to try, you can see that many other models, show the same kind of behavior if you allow more freedom, as I showed, etc. So this is typically, these plots are all the data combined. So DESI plus CMB plus supernovae. Typically that's what they show. And yeah, this is, by the way, the thing we are showing. This what do we call this? Non-phantom phantom behavior. So this is the best fit W. It's a very bizarre model. So in other words, we have, this is kind of a popular level picture. We have the best fit model is dark energy that increases with time, which is weird. And then doubly weird, it changes its mind and starts to decreasing with time. And so I think I've heard, I saw that Rafael Busso spoke here a couple of weeks ago, and he says that this must be wrong. This is too crazy. And I agree in spirit. This is very bizarre. At any rate, to declare that we ruled out, to have a paper with the title "Evidence for, departure from lambda CDM." In my opinion, that should be a very high bar, like 8 sigma or more. That should be a very, very high bar. So we were super careful to just talk about tantalizing, hints or whatever, some milder words. That needs to be high bar because, some other people talk in terms of the prior on lambda CDM. I just prefer to think about the evidence in terms of sigmas. At the same time, these results are very interesting. My personal threshold is 3 sigma to get excited about something, and there's more than one 3 sigma thing going on here, or at least independent, semi-independent things pointing. So at the very minimum, it shows to some inconsistency among data sets. So this is quite interesting, not that, should be ruled out somehow. Okay, so we prepared, the DESI team, Sesh, Nadatur, and Kushal Loda, and others, frequently asked questions. This is a kind of internal document that to help us think, and I'm going to now have a few of these frequently asked questions and answers. These are things to which we know the answers, we think. So for this audience, I think some of them are maybe obvious. I think not all are obvious. So here's the FAQ in no particular order. Are the data sets you're combining in tension? No, they're not in tension. Every time we combine, that's consistent. For example, even DESI BAO and supernovae are consistent in W0 WACDM. They are not consistent in lambda CDM, so we don't combine them in that case. But whatever we combine together is checked to be consistent. Is DESI data in conflict with the Sloan data? No, even at the level of individual error data points, even if you cherry pick data points, there's less than 2 sigma. Also, we think that it's not wise to go back to Sloan anymore. Just a moment. In DR1, we compared to Sloan, and we went back and forth. And Sloan was better at low Z, I think, and we were stronger statistically at other Z. But in DR2 now, DESI not only has more data, but is a more sophisticated analysis. And so we don't think it really makes sense to go back to SDSS. Yes? It could be, but this is a cherry pick data point, right? This is a single data point. Yeah, it might, I thought it might be 2.5 sigma, but you will find, if you looked at all the data points, you will find 2.5 sigma. So I think that's right. They're not completely lined up, but we did this thing where we applied Sloan pipeline and DESI pipeline, and we now think that DESI pipeline is just more sophisticated. So I think that's the bottom line, that there's no reason to go back anymore and dig up. Though, if someone wants to study, it's a good thing to study, potentially. But we think our official line is that there's no tension. Okay, this is a very common one from, often theorists, others, is this data point, that is LRG Z of 0.51 BAO data point in conflict with 2 lambda CDM? No, we checked, is it conflict with cosmological models, in other words? Is it away from other data? We checked this. In fact, this Z of 0.51 it was, I forget what, it was 2.5 sigma, now it's 1.5 or something. It went closer. From DR1 to DR2, we went back closer to the other data points, but we are pretty sure that this, result is not due to any one data point. I think that's a pretty firm statement. No one data point is responsible for it. And here's my favorite. Is it to quote the paper from the archive, unsettling coincidence that we find W of 0 minus 1 at 0? So let me explain this because maybe this might be a little hard. So if you look at the best fit model, where it crosses the phantom divide is also where W is best measured. So all 2 parameter descriptions of dark energy have the so-called pivot, the redshift at which the error bar effective is narrowest. And that's called the pivot redshift. And here the pivot redshift, which is the narrowest error bar, if you look at the error bar, coincides with a place where W crosses minus 1. So the question is that quote unquote unsettling? The answer is definitely no. First, to me, in a vacuum, to me, it's just a coincidence, okay? Coincidence. Second, actually, W at this Z pivot is not quite minus 1. From the best fit data, it's 0.954 plus minus this. So it's about 2 sigma away from minus 1, actually. It's not quite minus 1. And third and most important, if you have W0, WA model, and if you have CMB distance prior, like the distance from the CMB, that agrees with lambda CDM, then you are preferentially pulled into precisely this situation where you have variation in W because you're in W0, WA that crosses the pivot, that crosses the phantom at the pivot point. That is to say, when W of Z is -1 at the pivot point. You're preferentially, this is what happens, and this was pointed out by Eric Linder in 2007. So not only is it a coincidence, it's actually quite a favored coincidence that this happened. Yeah. Yeah, you're right. I agree with that, I think. Yes, you're right. I mean, you can now split hairs on this for a long time, but I think I agree with you that you can reframe this, why is lambda consistent with? You can try to chase down the origin of the sin, but yeah, I agree. You can phrase it that way. Sorry, so people on video, I don't know if somebody watches this in the distant future. Thomas asked here whether CMB distance agreeing with lambda CDM can be considered a coincidence in the first place, and I think that's right. You would say that that's a quote unquote. These quote unquote, these coincidences are notoriously hard to quantify, right? So that's yeah. But anyway, this is a further. That's right. Okay, so that was frequently asked questions. So now, in what follows, and then I'll end after this. I have 5 facts about these hints for dynamical dark energy. Some of them are more obvious than others, I think, and Hubble tension. And yeah, they're not like mathematical facts. They are more statements that are quite likely to be true. They're not quite theorems. Okay, so I'm going to go through them at some, again, some of them are more obvious than others. And this hopefully is useful in our thinking about what the data is trying to tell us. So fact number 1, I think I said this already, preference for W0, WACDM doesn't come from not just any one data point, from any one cosmological probe. And this table is potentially useful. So a really big peace of mind is that if you're a supernova doubter, if you don't use any supernovae, you get 3 sigma, okay, some tension with a lambda CDM. If instead you use DESI and DES year 5, no CMB, you get 3.3 sigma. And this is a really relaxed one in that it only uses DESI and DES year 3 times 2 analysis, 2.2 sigma. Not shown in this table is if you use supernova from the dark energy survey alone, they show the more than 2 sigma. So supernova alone, not DESI. They show more than 2 sigma for, now you might say supernovae, I don't like supernovae, that's fine. Then you go back to one of these cases without supernovae. So it's hard to count how many independent pieces of evidence, but it's more than one. It's more than 1.0 independent piece of evidence that, there's some tension in the sector. To me, this is quite exciting. If it was just DESI or just one thing, then it would be okay. I don't know, let's double, triple, quadruple check. That's fact number 1. Fact number 2, this is a really useful one, kind of obvious, but useful. Because a lot of people, and even some unfortunate press releases, I think they talked about the slowing down of dark energy. So dark energy would be slowing down, quote unquote, if W is greater than -1. So we don't claim we have evidence for slowing down of dark energy or phantom dark energy or anything like that. All we have some tension for is disagreement with the lambda CDM model. You could independently test slowing down dark energy and phantom, but you would necessarily get weaker evidence because kind of your evidence is more or less maximized if you talked about this departure. In particular, we don't have very strong evidence for phantom at all. And the reason I know that is a number of people wrote papers where we discussed scalar fields. And the rolling scalar field, your best fit is forced to be like this green curve and then starts hugging -1. That's your best fit. And that best fit is not quite as good as the W0 WA, but it's kind of most of the way there good. So that tells me that the evidence for the phantom part is probably very weak. I don't know what the evidence for the slowing down is. You can calculate that from some of these papers. But this is, often people kind of cherry pick the parts of this and we don't have evidence. We haven't checked, that you can calculate evidence, but the only thing we are claiming is this departure, this whatever 3-4 sigma departure from the lambda CDM model. Maybe that's obvious, but I hear a lot of this. So, right, sorry, the answer was no for either of them. And I just said this in words. The evidence for individual parts of this will be necessarily weaker. Fact number 3, preference for dynamical dark energy comes from the so-called curvature and distance. And Satya showed a lot of detail about this in her talk I showed, and we have a very complicated plot in the DESI paper about this. But I prefer this very simple plot made by Arnaud Dematia. It's simple, so you can kind of, it's much easier to see what's going on. So the vertical axis is the measurements of isotropic distance relative to some fiducial. This is the ratio. So these are the two kinds of distances, isotropic and the ratio of the two distances. And then the third is the supernova magnitude. And the flat line at unity is a lambda CDM. This is best fit lambda CDM model. The orange curve is the best fit W0WA model. And what you see is now you can almost try to do kind of chi by eye. The reason that the red curve is much preferred to the black horizontal curve is that the data go up, down, up. You know, you can see there's not data in every panel on that, but so this curvature in the data cannot be well fit by either lambda CDM or W, but you need W0 to WA or another equivalent model that has enough freedom to show. So this is, I think, a really nice way. We have a much more complicated plot with gazillion curves in the DESI paper, but this to me brings back home. Now that was the red curve. Now the orange curve is interesting. The orange curve is same thing, W0, WA, by dropping this low redshift supernova point. This low redshift supernovae have gotten a lot of flack. People, I think, understandably have some doubts about them. They are historical because the volume of the universe at low Z is small. There aren't many supernovae at low Z. So, you know, we go back to really old supernovae for this. And in the near future, Zwicky Tangent Factory, I think, will massively update this data point with data. But if you just drop this data point, then you go from red to orange curve. And you can see that red and orange look similar. Chi-squared is different, but they look similar. You might ask, why does the red and orange look similar if this was the only point at low Z that was kind of doing the up thing and now it's gone? And the reason is that we are not showing the CMB prior in this plot, and it's the CMB prior that conspires to keep orange close to red, even if you remove this low Z. So there was a lot of discussion about this internally and externally, and we don't think removing individual data points from other people's observations is a good idea. Who are we to say supernova data Z of 0.1 we can't trust? It's a supernova people's job to tell us if we can trust it or not. But anyway, if you choose to remove this data point, then you get, again, similar result with now slightly weaker chi-squared for departure from lambda CDM. That's fact number 3 out of 5. Fact, yes, Blake. Yep. So Blake is saying that there's tension, I'm repeating it for other audiences, at 3 sigma level, and this data point moves it to 4 sigma. I haven't checked that exact statement, but you might well be right, yes. So that is something to consider for sure. You're right, 4.2 sigma only obtains in this golden combination that includes DES year 5 supernova in particular. So that's actually, that's a good point. I'm not gonna disagree. Yeah, that's a good point. And 4 sigma, of course, is a much more powerful thing than even 3.5 sigma. Okay, now we are kind of splitting hairs, but yes, I agree with that. That's one thing we'll all agree on it. That's an extremely important redshift supernova low Z, right? I think that's pretty non-controversial. So cleaning that up, getting more data is going to be really, really important. Okay, that's, I think, that's been known for a long time in cosmology and remains true. Fact number 4, as far as I know, and can tell, Hubble tension, Hubble and this, let's call it dark energy, evolving dark energy, are completely different things. They're not related. Despite a lot of things, despite the paper 2 days ago on the archive that claimed the opposite, that's not correct in my opinion, and I can discuss why later. Here's the simplest way to see this. In W0WA, you measure H0, and you get lower even than before. You get a range between 63 and 67, depending, I think, on some assumptions. You get an even lower H0. So you don't at all move to 73. You get the worst disagreement in the difference, but then the error bar is bigger. So I don't know how sigmas of the tension change, but you definitely don't improve Hubble tension if you go to W0WA. So as far as I can tell, they are two different things, which also is kind of an exciting thing. And last fact on which I have plenty of time, I'll spend a few minutes on this, a few slides. This is kind of a known thing, I think, that, well, okay, let me make the statement first. It's almost impossible, almost like a theorem, but not quite a theorem. It's almost impossible to relax both Hubble tension and remove this evidence for dynamical dark energy with a low Z model. That is, I don't mean remove evidence, I mean to explain, to fit Schu's data and to fit DESI and all that data, to fit all data with a model at low Z is almost impossible. All the fits are bad. I think this is a known fact. Evstatiou wrote a paper with something like this. Vivian Poulin's group had a paper, Valerio Mara. There were a few papers about this, but this same student, Prakar Bansal, and I set out to understand that. So we try to understand this first better for ourselves and then maybe better. I don't think this is known to everyone in cosmology. It's not maybe super clear. So I have a few slides that maybe help clarify why this is true. So first of all, this is the supernova. This is the plot in where supernova magnitude, the distance modulus is on log distance is on the y-axis versus redshift. And this is a BAO data in solid and supernova data in open. And now the supernova data, there are two sets. They are identical, but they are vertically moved. The reason is that in supernova business, you have a choice of selecting absolute magnitude. So you have to marginalize over absolute magnitude, sometimes called capital M or script M. It's really a combination of absolute magnitude and Hubble constant. So you don't measure Hubble constant with supernovae if they are not anchored to Schu's. So if the supernovae are not anchored to Schu's, normal supernova, no anchor like the ones we used to discover dark energy in the late 90s, normal, Pantheon data set. There you have a choice to move it up and down, and that's purple data points. And now you have some model that fits pretty well. I think the dashed line, this is on the CDM. But now if you anchor to Schu's, if you use Schu's measurement of the Hubble constant, now this is selected for you. You don't get a choice anymore. And now you get supernova data points that must lie here. And now you can see that it's impossible to have a model that goes both through the supernova data points and the solid BAO data points. And the reason is you have the overlapping range. So in this range from here to here, you'd need to simultaneously fit these points here and those points there. And so that's like impossible in any reasonable model. So this is kind of known already, but we are trying to clarify this. And so in the next few slides, I have a little bit more clarification about what exactly do you need to pull off in order to, if you believe Schu's data, if you believe other supernova and BAO data, then which thing can possibly fit everything? And the answer is nothing at low Z other than a really kind of crazy and trivial model. Yes, question. How did I translate BAO measurement into mu? So yes, so mu is like a log of the distance, and BAO measurement is kind of a distance. Now it's distance divided by the sound horizon. So I believe we take we probably take BBN prior here to solve for the sound horizon, and then BAO gives you distance. And the y-axis is just log of a distance. It's log of a distance divided by distance, some fiducial distance. Yes? No. Do I count curvature as low redshift? No. Curvature, this is a little bit of a tangent, but let me spend 25 seconds on it. Curvature can exist, non-zero, and we heard about it. Some people are excited, open universe, positive omega k. In DR1, we found that our W0 WA results are almost unchanged if you add omega curvature to W0 WA. This made us actually drop omega curvature from analysis in DR2. So we don't think curvature is, I don't know if curvature is low Z or not, but curvature, I don't think curvature does, well, I don't know, I shouldn't speak when I add Schu's. I don't know that we've checked that, but without Schu's, normal, BAO and CMB, you get the same W0 WA with or without curvature. Can you say it louder? Sorry. Oh, it helps the H-naught tension. So now you're talking in units of H-naught tension. Okay, that's interesting. Yeah, I don't have, yeah. Well, I'd be curious, this is a helpful comment, because I'd be curious, I'll show a few delta chi-squared numbers soon, and they are very bad except for completely like trivial but bad model, which is very good. So I'm curious where curvature falls on that range of chi-squared, because it's down to the numbers now. But thank you, that's a good comment, the omega curvature. 2.2 sigma favored. Okay. Yeah, I'd like to also know the delta chi-squared, because that's now the unit I'm used to. But yes, yeah, that's a good comment. So I'm going to show a few more illustrations. Is this kind of clear to everyone, this plot? This is quote unquote known, but sufficiently confusing, at least to me, that we are writing a paper about this, trying to clarify what's going on. So I'm going to show more of this same graph, except a slightly different. So this is the same graph. This is a log of a distance as a function of redshift. And I'm going to show a bunch of builds now. In every case, the horizontal line at 0 will be lambda CDM, and then there will be a different line with a different model. And this is a model that clearly doesn't work very well. Delta chi-squared is only -5, so it fits chi-squared by 5 better this is with shoes, right? And so we here distinguish Cepheid measurements from other supernova measurements. In a moment, you'll see why we do this. These are Cepheids, this is other supernovae. And the confusing thing with this plot is that the data change as you change the model. And the reason the data change, normally data are fixed and model is changing, right, in any plot you see. The reason data change here is that, again, that dreaded script M. So the absolute magnitude best fit is different in this model and in this model, and the best absolute magnitude best fit enters kind of into the data. So this is specificity of supernovae and script M, that when you change the model, your data points actually change. You can think that through a bit. I know it's a little bit surprising at first, because we never expect, but this is what fundamentally, if you plot this, and if you plot other quantities, we went through this. There's no good quantity to plot, because you can put quantity in which supernovae are fixed, but then BAO data shift, and that you definitely don't want. That's too confusing. So going from one, you can see not much changes. How gray curve goes through gray points, or purple curve goes through purple points. In each case, you miss this point very badly. This shoes normalization, really. This is Cepheids. So you don't do very well, and you only improve marginally. And also, you can even try crazier things. We haven't tried odd models, but here's a sharp step in the Hubble parameter. And the sharp step in Hubble parameter is a pretty extreme model, but for the reasons I mentioned already, it won't work. And delta chi-squared is only -1. And this is a sharp arbitrary step at the best fit redshift. So this is a best redshift at which you can have that step, and it doesn't work. What does work is the scheme, which I'm going to show next, where you shift these points but don't shift the other supernova points. And that's the shift in this one, in the absolute magnitude, the redshift of about 0.01. So if you do that, you can see that you basically renormalize the Cepheid data point and don't do much with the others. And so you get a much, much better field. Delta chi-squared is -37 in this point. So this is a model that fits. Unfortunately, this is a really trivial model in that it basically takes out shoes data. By saying I can shift this data point and not the others, it's the same as saying I'm going to ignore shoes data. I'm going to move shoes data wherever I need it to be. And so if you do that, obviously you remove shoes. Now you have a good model. You have a much better fit than if you had shoes. So this is the only model that works, except it's a really trivial one. It takes this from the equation. It takes shoes data out. You can say, okay, now let me do that model and add W0, WA, you get the same. So adding further features doesn't change that. You get also good chi-squared only because you've taken out shoes. And this is, if you're wondering what's the best redshift, to input that step. So this is a step in the absolute magnitude, and the best fit is 10 to the -2 redshift. Regardless of what you add, if you do, what's the other change in the model is. It's a crucial thing is that you basically took out shoes data. So this corresponds to new physics in supernovae that happened when dinosaurs lived 150 million years ago. Dinosaurs are around. physics of supernova changes, that's that time in the history of the universe. That's a really bit of a crazy model, and it really corresponds to discounting. So the only ways to change at low Z to fit the shoes data and other data is either this crazy M step or break distance duality relation between angular diameter distance and luminosity distance. And trivially, if you break duality relation, you can independently move supernova data up and down and BAO data up and down. You have new degree of freedom. There are two different kinds of distances that are not related. And then, of course, trivially, again, you can fit shoes data and other data. And people have written papers about this. That only leaves high redshift solutions, but as you know, as this audience knows, they are very high-tuned. They are very fine-tuned, like the changing the sound horizon. But for low Z solutions, it's almost a theorem that there's no good solutions to fitting both shoes data and the BAO and CMB. In conclusion, preference for W0 WA is driven by quote unquote curvature in distance of Z measurements. Why there's that curvature, I don't know, but there is. This preference is not due to any one single data point. It's not even due to any one measurement or cosmological probe. And it appears to be very robust with respect to dark energy parameterization. That part, at least, it's robust. Hints, this also evolving dark energy thing appears to be independent of the Hubble tension. To claim evidence, however, should require a very high bar. I agree with a whole bunch of people who feel the same, I think, in some other language. It'll be very exciting to see what's forthcoming. This is DESI-centric list here, full shape analysis from DR2, which is a lot more complicated than BAO is coming out, I think, later this year. Bispectrum alone, and then power spectrum for bispectrum is coming soonish, and 5-year data, even more vaguely soonish, but all relatively soon. And then I talked about ZTF importance for low redshift, Simon's observatory, cross correlations. I'm dying to know what Euclid and Spherix find. Very, very curious how that works out. I should say one more thing. This is a familiar to everyone laundry list of things to come. Lots of talks have this. But there is only one, in my experience, there's only one golden probe from this DESI so far, which is the BAO, because it's really relatively simple compared to these other things. Many of you work on some of these other things. They're a lot more complicated. And they're really effectively more assumptions. So BAO is really very clean. And that said, it'll be very, very interesting to see whether these measurements confirm or at least are consistent with those findings, and then especially what these other surveys and measurements find. Thank you. I had frequently asked questions, they were answered. Like, yes. Yeah, so the question here by Blake is whether negative neutrino mass can be considered as a proxy for new physics and whether it's similar to W0 WA also being proxy. Yeah, so now we are, you put it in a more reasonable way now, and so I kind of partly agree, but why I am a little bit allergic to it is that when people implement negative neutrino mass, they of course need an ansatz, because you can't stick in a negative number there in the equations. And the ansatz is just like a completely made up thing. It's an extrapolation of how angular power spectrum, to my knowledge. And I really am not a fan of that kind of thing. You're right, it's because it's an unphysical region, so we don't go to negative, not that we needed to go to negative omega matter, but we probably wouldn't have gone to negative omega matter to describe new physics if we had to, we would have done something else. So I don't like the framing, but at some level at the same time, you're right. I don't know that it's equivalent. There are people who would vehemently disagree that it's same as W0 WA because W0 WA is quote unquote physics. This is like a long discussion that cannot be won either way. But I think just I think I have a problem just with the fact that it's a physically positive parameter that's somehow being forced to be negative. Had it been some other neutral thing, maybe it would have been okay. But I see you have a good point. It's a proxy to see what data trying to tell us, and I think that's what people who wrote those papers had in mind. It's Matthias. Methodology. Yeah. Yeah. I am unfortunately not the right person to ask, but I can give you a very high level overview. It's not new in DR2, I don't think. It was new in DESI, so to speak. So it was small improvements as we go along. And as you have more time, as time goes, you put new ingredients. But a lot of checks are done to see where I think fiber collisions is a very big factor. So those fibers, those little sticks that are looking, they have to avoid each other. And when they avoid each other, they create a selection function because if you have two galaxies nearby, you cannot observe both of them. There's some kind of avoidance selection function that needs to be modeled. That's a very complicated problem. That requires multiple people. So that's one kind of thing to make sure that those effects, for example, are under control. So it's a very nitty-gritty thing. Right, extraction of the peak from the correlation function. So the correlation, yeah. Yeah. No, that I can say a few things about because I tried to do it once and I was surprised how more sophisticated it was than what I thought. I think if you flew in and if you didn't know anything and if you just fit a parabola, I think you would have done maybe an okay job. But the way people do this is they fit a broadband like a power law background, and then a peak, and then extract. And so it's a fairly complicated analysis that's been tested to death. And it's even been tested, one of my grad students tested for modified gravity even to make sure it works. So how you know it works, you have a synthetic everything. You don't need a simulation. You start with BAO. You generate BAO data, the data vector. With some model, it could be even modified gravity model, and you extract the peak and you try to see if you're consistent in your cosmology constraints with the input model. So this has been beaten to death for the BAO peak. It's fairly sophisticated. The main thing is adding this background, fitting the background like a power law P of K with a peak, and people have done that. So this is outside of DESI, this has been worked out. I think Boss and other people. It's a detailed thing that's like a knowable problem that can be solved completely. Yeah. No, that's right. It's not immediately obvious, sub-percent level, 0.1%. So it's not immediately obvious it should work by eye. And you can wonder about, the slight tilt. And so this requires full end-to-end, starting from data vector test. And this has been done, like I said, not just for lambda CDM, but even for modified gravity models, like Horndeski models. And it works okay for the current near future precision. I don't know, distant future precision has to be revisited. Yeah, not obvious at all that it works, but it works. Yeah, extraction. It's not our main worry at all. This is at the back end of the worries. I think fiber collisions are one of the bigger worries. There are some other things, but much fewer worries than if you do full shape. Then you have many more worries. Yes, Thomas.
Principle, it means that all the testing that you did to extract DAO, you have to check that whatever you did is also correct for a BAO peak that was generated with negative freedom. So have all these things then also across the other bin, or what subset of data involved in.
I told one of my graduate students it'll become the question is about negative neutrino mass and test. So sorry, say it again. What do you need to do? Did you say? You need to do in W0 WACDM as well. Yeah. In every model, yes. Yeah. So the reason I'm familiar with this is one of my grad students wrote a big tortured paper doing this for Horndeski models, which is much more freedom than any even W, and it worked even there. It wasn't obvious. The normal, procedure that's originally developed for lambda CDM would work there, but it did work there at the level of DESI precision. So it works for W. So again, not obvious, but it works. Negative neutrino mass, I told one of my grad students, I'll make it my life's mission to expunge negative neutrino mass. But yes, whatever model you test, if you're working in certain model, you need to validate that everything that you do works, has been validated in that model. One doesn't always have time to do it, but in principle, it should be done always.